Welcome back. In the following, we want to quickly talk about some deep learning frameworks, or more specifically, how they internally work. And indeed, as it turns out, nowadays there are a couple of deep learning frameworks available: TensorFlow, PyTorch, MXNet. And they all make it very, very easy to use or develop neural networks. We have really here this plug and play feeling, so to say, where you can plug together all these different modules, and then it's very easy to train these networks and to also deploy it and to apply it to new data sets. So it becomes extremely simple. And indeed, there are many, many open source libraries available, different tools which you can all integrate into these frameworks. I just want to quickly show you here with one tiny example how this looks like and what they are based on. And indeed, the core idea is that they are based on these computation graphs. We have seen these computation graphs already in the backpropagation setting, and here you see a similar illustration, so to say, how it looks like. It's more or less identical to what we have seen in the backpropagation, and just in a different programming language, so to say. And indeed, here on the right-hand side, you see how it works here. For example, in Torch, you can start by defining some variables, x, age, and so on and so forth, right, which you have defined here. You see also the different sizes, for example. So this is a vector, and these are matrices. And you also see that you initialize them, for example, here randomly, right? So the random initialization of this vector, and this becomes then a variable. And then you can really just apply operations on these data objects, on these variables, on these tensors, often called. For example, you can take wx and the x transpose, and you multiply these two, and this gives you a new object, as shown here. Or you can do the same with these two variables, right? You can multiply them, and you give it a name, which is called I2H, right? And then you can continue, right? You can take these two variables, the outcome here, these two here, and you can add them up. And you can then, afterwards, you can take the tanh of it, and this gives you another variable. Okay, so you see here, in some sense, the computation graph, it looks slightly different from what we have presented to you in the backpropagation, because here it's more like this kind of programming view where you're attaching the variables also here to the operation, and you see that we have this overwriting. So this is why you just have it below here. But you see that the graph itself is exactly what you have seen before in the backpropagation. We have a chain of operation we are applying to our variables. And so variables and operations until we get our final, let's say, final representation. Okay. So this is the computation graph we are constructing. And you see that this is indeed what this programming language supports. We are constructing this graph on the fly. And given this, then indeed, we can, for example, also just say we want to do a backward step on this. Okay, so we can here apply the backward function, and then we can do the training. Okay, and indeed you will do like a more extensive tutorial session and a homework exercise where you will really learn how to use these frameworks and how to build up your neural network model, so to say. So these frameworks, again, do not only support constructing this computation graph, but they also support doing backpropagation already through this model. Okay, so you don't have to care about this functionality of implementing backpropagation by hand. So indeed, what we have seen before, these modules, right? These are all these internally different modules, right? The addition and the tanh and so on and so forth. Internally, they implement always like this forward pass, which is the actual operation, and the backward pass, which is like computing these corresponding derivatives, right? And as long as you are staying in the standard world of what they already support, you don't have to care about this at all, right? You can just invoke these functions and you use it as you want to apply the function only, and then the backpropagation is done automatically. If you want to develop a new function, a new layer, a new module in general, then of course you have to implement the forward and the backward pass. Okay. Otherwise, however, you can just do Lego, and this is all what you need to do training, so to say, of your neural network. Okay. So one point I want to discuss in more detail, and again, more important, is that you really get some hands-on experience in your homework exercise, right? I guess it's really the best to play around hands-on with this. It's rather dry to just present it here on a slide deck, so please really download it, play around, do the exercises, do the homeworks to get really an understanding how this works. One point I want to mention, though, is the following. There's a small distinction between so-called static and dynamic computation graphs. So what does it mean? So in the static version, of a computation graph, you first define the full computational graph, right? And then it can get compiled, so to say. And then later on, you can run this computation graph with data, so to say. Meaning you first define, let's say, your neural network, and then later on, you just have to feed in data, and it gives you the result, and you can do backpropagation and so forth, and so forth. And the contrast, there's also like the dynamic variant, the dynamic computation graph, where it's, so to say, defined on the fly, so to say, defined by running, right? So the computation graph is more or less, as we see it here in the animation, it's constructed while the code is executed, so to say, right? So this is a small difference. And what is the difference in detail? What is the pros and cons of this? The pro of a static computation graph is that it can be optimized by a framework, similar to some source code, right? In the source code you type, and then you have a compiler which can optimize your source code. And here you can, for example, think about optimizing your computation graph. Simple example, which some of you might know, if you do matrix multiplication, right, you have three matrices, A times B times C, you have different choices how to multiply, right? You can first multiply A and B, and then the result is multiplied by C, or you first multiply B by C, and then the result is multiplied by A, right? And of course, the order of multiplication might matter how expensive your calculation is, right? Because, for example, A times B might be a very big matrix, right? And then, for example, with C, it might become again very small, while, however, B and C might be small matrices, and then multiplying it with A is also very efficient, right? So the order of operations, this is a classic problem in efficient algorithm, the order of multiplications matters how many operations you have to do in a computer, right? It might be more efficient to first multiply these two, for example. And this is what you can do in a static computation graph. In a static computation graph, you first define what you want to operate, what is the operation, A times B times C, and then the compiler can see, okay, wait a second, I first evaluate this and then multiply with A. In contrast, right, and a static dynamic computation graph is really doing this on the fly. And since then, A is first, then B, then C, it would first multiply A with B and then the result with C, right, because it operates from left to right, so to say, on the fly, okay? So you see static computation graphs give you some potential for optimization. So why then using dynamic computation graphs at all? So one reason is that, that it's often easier to debug in these codes. This is just a very technical argument. The other point is that for some architectures, you cannot really construct a static computation graph a priori. Specifically, if you're looking at sequential data with RNNs, the operations you are doing in an RNN, we didn't talk about this in detail here in this lecture, but just as on a high level, they often depend on the length of the sequence, right? So the longer the sequence, the more operations you're doing because you have to process every element. So a priori, you don't know how long your sequence is, right? Because it can be a short sequence or a long sequence. In this case, you cannot really construct a static computation graph in a nice way if you don't want to do padding, for example. And this is the advantage of these dynamic computation graphs. They can easily handle this RNN settings, for example, because they can on the fly adapt, so to say, to the length of the sequence. Okay. So as a side remark, all the major frameworks indeed nowadays support dynamic and static computation graphs. Dynamic computation graphs often also for developing, for doing your development, debugging of your code. And they are much more natural to work with then, right? Because they are processing it in the order how you code. But then often they also have this static view if you want to, for example, deploy your model, right? If you want to really use it in some production system, then of course it makes sense to speed it up, okay? Good. So this is what I wanted to say here for these frameworks. Again, please download them, play around with them, because that's the best experience you can get. Just hands-on experience helps. And then finally, a few more words to some tips and tricks, so to say. And as you can imagine, what we have shown you here is just really a tiny portion of neural network engineering and research, right? There are much more different principles you want to use to make this all work. So it's not as easy as just writing it down and then it will work, but it really requires some work to make it running for your specific use case. And one point I want to mention here is the so-called batch normalization. We mentioned it already before. In the context of like generalization, for example. So what is batch normalization? So batch normalization is designed for stabilize, again, the distribution of the activations, or simply speaking, to allow better training, to make the training more stable, to to achieve that even a deep network can be trained. Okay, and what is the idea or the ideal vision we want to achieve? So intuitively, what we want to do is we want to do a whitening in every layer, so to say, in every neuron. Whitening means instead of feeding in the raw signal to your layer, you are first normalizing this. Okay, so you're subtracting the mean and you are dividing by the variance or the standard deviation plus some epsilon to avoid division by 0, right? So this is like a whitening, right? We have seen this at the very beginning of this lecture where we said it's always a good idea to standardize, to normalize the features. And intuitively, this batch normalization is doing this. Okay, why it's called batch normalization? It's called batch normalization because it's often done also only on the batch, right? You know, we are doing stochastic gradient descent usually, so we don't operate on the full data, but we're only operating on a subset, on the mini batch of your data. And this is why usually this here is only applied on a batch. Okay. So this batch normalization is applying the statistic on a mini batch. Okay, so we are subtracting the mean and divide by the variance or standard deviation to normalize our data, and then this data here is fed into our activation, so to say. Okay, so there are a couple of more points which are done in detail in these batch normalization layers. So there's one problem here, right? So during training, of course, you can do this normalization in principle, right? You can do this normalization because you have then your batches and you can compute the mean and the variance, for example. However, if you want to now do a test phase, right? You have like deployed your model, you get a new image in, of course, then you have a single image, right? And for the single image, you don't have the mean and you don't have the variance, right? So technically, you can't really compute this, right? So what you then actually do in practice is that during the training, right, during batch normalization training, you're actually often computing like moving averages of these statistics, right? Moving averages means you monitor, so to say, what is the mean and what is the variance during training, right? And then you have stored this information, and then once you deploy your model, right, you know what is like the average, so the mean, the average mean, and what is an average variance during training, and then you use this information when you apply this model. Okay, so please keep this in mind. Batch normalization then means for the application phase, usually you have to get some estimate for these statistics, otherwise it doesn't work. And then finally, there's another aspect. Often this batch normalization is often also then not directly done on this normalized data, but often we are also having like two additional parameters. One is for the scale and one is some offset to, again, essentially counteract what we have reduced before, right? Because before we have removed the offset and we have so normalized it, so we get rid of the scale, right? And this might lead to like a layer which is not as expressive as before, right? Because we essentially get rid of, we have this shift always removed. So this then, instead of operating on this normalized data, we indeed operate on this scaled and shifted back data, so to say. So why is this still now different, right? It's still different because these here, right? These here are two global parameters, right? These are just two parameters which are learned with our neural network, right? In contrast here, if we would use the unnormalized data, this is just completely data dependent, right? And these are here two parameters. So these are two different aspects, right? So this is like very data dependent on a specific batch, while these here are global parameters. Okay, so they behave differently. Okay, and again, right. So this is all done after a layer, for example, but before the nonlinearity. Okay, so meaning we, for example, do like some affine transformation. We can normalize it. We can scale it back, right, and then so we have our input, we normalize it, we might want to scale it back, right? And then it's fed into the activation, okay? So Y here is fed into the activation, okay? So this is how we can normalize always our input with respect to this specific batch. And so why does it work? So long story about this batch normalization. So why does it work? Indeed, it turns out, and there's not a full understanding yet, it turns out that indeed this batch normalization smoothes out the loss landscape, right? If you look, for example, here at our training, right? So here you see the steps in our training, and here you monitor the loss, which you should always do, right? Always monitor the loss, how it behaves. Then you see if you do standard training, the loss varies a lot, right? The loss varies a lot because you're doing stochastic gradient descent, right? And the data you have in your batch might be very different every time. However, if you do batch normalization, you see that the loss landscape is much more smooth, okay? So here you see the loss. Here you see the change in the gradient, right? So what is the fluctuation in the gradient based on some norm, right? Let's say you measure the distance between, so the norm between the last and the current gradient, right? Then you can monitor the change in the gradient with standard training and the change in the gradient with batch normalization. And you see that the gradient is more smooth, right? This is not the gradient, but the change in the gradient, right? The change is more smooth. So the gradient behaves more nicely for training, right? Because it's not fluctuating around all the time, okay? And you again see it here also in the loss curve. So long story short, batch normalization often leads to more stable, thus more predictive gradients, which might help training. As you see here, the loss behaves nicely, okay? Because you're normalizing your data, your batch every time, right? This makes it much more stable. So this is one, let's say, trick or tip which you might want to use when you see that your training doesn't work. Batch normalization might indeed help you to achieve better training. And as said, right, training a deep neural network is a challenge, right? Just writing it down is not so hard, but really getting it to train, to learn, that's one big challenge. One other point I want to mention here, because that's also a very prominent component of modern neural networks, which is called a skip connection. So intuitively speaking, a skip connection is on a very high level the following. So if you have some data, and let's say you apply some, layers, let's say convolutional layers, a skip connection, intuitively speaking, is just that the input is skipping this, right? That's the name. It's skipping is directly jumping to the next layer or to the layers later, right? So the input is, so to say, forwarded, takes a shortcut, and then it's also reused, okay? So one specific instance of these skip connections are these so-called residual connections, right? So what I just said is that you're skipping multiple, usually 2 layers, and then the information is reused, so to say, right? And another setting is these so-called highway networks. Here you see it more clearly on a technical level. So a highway network is essentially doing the following. So let's say you have here specific information of a specific layer, right? You have your current X input signal. You have here some specific layers like these 2. And then you have a so-called gating mechanism, right? A gate means it tells you whether the gate is open or not, right? So it's some number between 0 and 1. And this highway network, you see that you take your signal, and again, this is trainable. This gate is trainable. Based on the signal, this gate might be open, it might be 1. Then you're using this information, right? And not this one, right? Because if t is 1, this becomes 0. But if the gate is closed, for example, so let's say this becomes 0, then this term kicks in and you're using x, okay? So you see with this highway network, you really are either using these layers, right? These 2 steps, right? Or you're using the original input signal, x itself, right? So you can decide whether you want to use x or f of x, so to say, via this gating mechanism. Of course, the gating is not binary, it's not 0 or 1, but it's some mix between, right? It could be 0.8 here and then 0.2 here. But you can imagine like that this gating mechanism decides whether you want to apply this layer or you don't want to apply this layer, right? So this is here. And the residual connection is essentially the simple form of it where you don't have any gating. You directly also use here this information. You can do, for example, a concatenation, let's say. Right, you use the transformed data and you concatenate it with the original data, and then you forward this to the next layers. Okay, so skip connections or residual connections are very prominent building blocks of modern architectures. And then finally, some more tricks before you really should get some hand-on experience. So one point is, at least at the moment, you should potentially only use differentiable operations because you want to compute the gradient, right? So these operations should be differentiable. Technically, you can also use non-differential operations, but we don't cover this here in this lecture. For this, again, look at our follow-up lectures. But of course, there are some which are very important, like the argmax, for example, or sampling from a distribution, right? If you want to do some randomization in your neural network, these are all operations which are non-differentiable. So at the moment, you don't know how to incorporate this. And again, you can look at our other lectures, but as a starting point, so to say, please only use differentiable operations or operations which are directly provided by this framework, so you can already do this backpropagation. So then another tip here is always try to overfit your model, for example, to a single training batch of your data, right? So to check that your model is, we call it here, correctly wired, right? So let's say you have a large collection of images and you set up like a neural network architecture. It might be a good idea to pick, I don't know, a specific subset of your data and see whether your architecture at least works on this kind of subset perfectly, whether you can achieve a loss of 0, for example, right? Because if this is not possible, even for the small training sets, meaning you cannot overfit, so to say, to this specific small training subset, then something is very, very wrong, so to say, right? And then you might reconsider the choice of your architecture. So in general, also, you should potentially start with small models, simple models, which are not too expressive to avoid overfitting. And then gradually you can add complexity, adding more layers, more neurons, other kind of components, for example. Potentially you don't want to start with too many parameters, right? Potentially you want to avoid like fully connected neural networks and use directly CNNs if you have images and so on and so forth. So start with small models and make them larger over time, so to say. So again, be careful about the properties of the activation function. We talked about this in detail, right? Specifically, the last layer's activation function determines what the task is, right? So for example, you should not use a sigmoid at the very end if your task is a regression problem where the domain is between 100 and 500, right? Then the sigmoid, of course, cannot capture this because it's only between 0 and 1, right? So be, again, careful about the last layer's activation function specifically. Of course, also the other activation function in the middle might play a role. And use as much as prior knowledge you have about the task and data at hand. Again, using what kind of layers you want to use and so on and so forth. And finally, also, I said it a couple of times, monitor your training procedure. Do not just let it run and at the end you see, wait a second, the performance is not good, but really do this kind of plots, right? Monitor over time, over your training iterations, how the loss behaves. Does it nicely decrease? Is it extremely fluctuating? Is it even divergent that it increases, and so on and so forth? Monitor this on the training data, monitor it at the same time also on the validation data, right? So monitor these two kinds of losses, how they behave. And in general, because it's also a lot of engineering, as you have already seen, you can read other material online. There are much more tips and tricks how to do this. It's still a bit of an engineering discipline, but as I already said, there are also principles how to automate this process, automate principles, neural architecture search will help you. But again, always be careful how your model behaves and don't really just use it as a black box and you hope that it will work. Just be very careful when using these principles. So with this, we are then at the end of this neural network section. So these two weeks of neural networks, of course, were just a quick glimpse on this. And as said in our follow-up lectures, we'll give you more details on specific principles. And there are, of course, as said, many more material online, and feel free to check it out. Here, just to wrap up, so what we talked about here in the second week was one specific architecture, the convolutions. We also talked about padding, strides, and pooling, so terms you should be aware of. We also talked about then specific initialization to avoid like vanishing gradients. We talked about regularization, standard regularization with 2 penalties, but also dropout, and quickly also hyperparameter optimization. Deep learning frameworks, again, please play around with them. Hands-on experience is the best you can. It's the best practice you can get here. And finally, some more tips and tricks like batch normalization, skip connections, and so on and so forth. So with this, we are at the end of this deep learning slides. I again thank you for your attention. As usual, ask your questions online, and we see us in the next videos with another topic which will talk about support vector machines. Thanks a lot. Bye bye.